Hello and welcome to the second vodcast on wave characteristics, looking at amplitude, intensity, and the inverse square law. The syllabus sections that we'll be looking at are, amplitude and intensity, it's the understanding the inverse square law, amplitude, intensity, solving problems, and there are two data booklet equations that we will be examining, and we'll also look at a couple of questions and what they can tell us about what the IB expects us to know. So amplitude should not be a new concept for you. The amplitude of a wave, x0. Now I've given it some x0, value of maximum displacement x, because I think that's the correct way to put it, but it can be a little confusing. And so the IB would actually like you to also know and use the symbol A for amplitude. Okay? Now, in mechanical waves, such as, for example, if we were talking about a sound wave or we were talking about a water wave, then we would measure this in meters, maximum displacement. For other waves, such as electromagnetic waves, then it would be the magnitude of the field. And the amplitude is going to be related to the amount of energy. If you think about a water wave, if you're making splashing to make a water wave, then the more energy you put into it, the bigger the waves are going to be. If it's a vibrating drum skin that is making a sound wave, then the harder you hit that drum, the more it vibrates and the greater the amplitude of the wave will be, and the greater the energy it will have. But the relationship is not a simple linear one. In fact, it is a squared relationship. So the intensity is proportional to the amplitude squared. Now, intensity we will define for our purposes as the average energy carried by the wave per second and per unit area. There are actually in physics a whole load of different varieties of intensity. Is it the intensity that as it's emitted? Is it the intensity that's received? Does it depend on a particular wavelength range or frequency range? Is it going through the process of human perception, which we'll look at later? But for IB purposes, all we really need to know is that this intensity, which will be the average energy per second, in other words, power per unit area, with units of watts per meter squared, that's the definition of intensity that we are interested in. This is the equation from the data booklet, and notice that they use A, and in this case, A means amplitude. The constant of proportionality depends very much on what it is you're talking about. So for a mechanical wave in a fluid, it will depend on the density of the fluid. It will depend on the velocity of the wave. So there are a variety of other things to consider if you actually want to calculate the intensity from the amplitude. But at IBDP level, you really won't be asked to do that. Instead, you just need to know that the intensity is proportional to the amplitude squared. And if everything else is the same, so for example, if you're talking about a water wave and you're not changing the density of the water, you're not changing the velocity of a wave, then you're just changing the amplitude, then you will have the relationship I is proportional to A squared. But as I said, we should be aware, you should be aware, that this is a very physics definition, and biologically, things aren't quite so simple. For example, if we look at how the perceived brightness, how you observe the different brightnesses of an object, depending on the intensity, that will vary. If you look at stars, I've got Pogson's formula down here, which looks at a measurement of how bright stars are based on something called the magnitude scale. And it's a logarithmic relationship between the intensity of two sources, because an object that looks twice as bright, a star that you would say is twice as bright as another star, for example, will not be twice the intensity in terms of units of watts per meter squared. Similarly, your eye has a response. Here are the responses of the cones in your eye, which detect the different colours, red, green and blue. will have an effect as well. If you are seeing light of 400 nanometers, then it will appear fainter than light of 450 nanometers, simply because it's outside the spectral response of your eye. This is what your eye can perceive. This is the visible part of the spectrum, as we saw previously, which has evolved to take into account the fact that sunlight covers its maximum output during this range. So your eyes evolved to make use of the light available. Your hearing as well. Different, notice the logarithmic nature of this scale, the intensity scale, compared to this linear decibel scale. Exactly what decibels are and how to use them is outside the scope of this unit, but just be aware that a decibel is itself a logarithmic scale. So 40 decibels is twice as loud as 20 decibels, but that's 2 orders of magnitude difference in terms of intensity. And also, this is how your ears respond over different frequencies. The dip here, the lower part, is actually the most sensitive, and that's approximately 2000, 3000 hertz, which is about the frequency of human speech. So your ears have evolved to make use or make most sensitivity of the kind of sounds that you're most likely to hear. Now, if you have a source of radiation, be it light, be it sound, that's spreading out in a spherical way, as most sources will do, over space, then it will obey something called the inverse square law, which is just a consequence of geometry. In that, if your distance from the source of the wave doubles or triples, then because it's going out over the surface of a sphere, 4 pi r squared, then the energy spread out over, if it's doubled, 4 times the area, if it's tripled, 9 times the area, which means that the intensity is proportional to the distance squared. So inversely proportional, so 1 over distance squared. I said that the data booklet is a little bit confusing on this point, because here this is very much, it means sort of received intensity, the energy of the wave, not the energy of the source, not the emitted energy, not the emitted intensity. And in this case, which is why they want to use A for amplitude, is because they're using X for the distance. It's a little bit confusing. If you look, an application of this is to going back to what we were talking about with stars, and this comes up in the astrophysics unit. In astrophysics, we have concepts called luminosity, which is the emitted intensity. It's the power per meter squared emitted by the star or galaxy. We have the brightness, which is the received intensity, which is the intensity, the power per meter squared, which is measured here at the Earth, and which depends on the luminosity, the emitted intensity, divided by the distance squared, 4 pi distance squared, because it's just spreading out as a simple sphere. And this is very, very useful if you know the luminosity, which, well, when we do the astrophysics unit, you'll find out how we can actually measure or determine the luminosity. You can measure the brightness, and you can rearrange in order to find the distance, which is a very useful thing to know. In terms of a couple of questions, not from the astrophysics unit, these are core standard level questions. Here's one, which graph shows the variation with amplitude of the intensity I for a wave. Okay, so we know the relationship is I is proportional to amplitude squared now, so we can identify that as the correct graph. Question 2, the orbital radius of the Earth around the Sun is 1.5 times that of Venus. What is the intensity of the solar radiation at the orbital radius of Venus? That's actually a more tricky question. Many people didn't get this one right, I don't think, when it was asked. And I think the reason for that is they're like, well, what's the data? And I'm pretty sure a lot of people didn't realise or forgot that the solar constant, S, is actually in the data booklet. Now, the solar constant is how much energy you get from the sun. That definition we'll be looking at in the energy production unit. So at the radius of the Earth, you get 1.36 times 10 to the 3, or 1.36 kilowatts per meter squared. That is the intensity. Knowing that, you're in Venus, which you have to know. This is a good question. It combines lots of different things. But it tells you that the Earth is further away than Venus, which I'm kind of hope you know anyway. So obviously the intensity is going to be greater near to Venus. That instantly eliminates A and B because they are less. So is it going to be 2? Is it going to be 3? Well, it's 1.5 times 1.5 squared multiplied by 1.36. Don't forget you don't have a calculator in this. You're not expected to do complicated calculations. But 2 is too little. It's going to be greater than that because over 2 times 1.36 is going to be greater than 2. So the actual answer works out to be, I think it's about 3.06. So 3 kilowatts per meter squared is by far the best answer. Okay, so we've looked at amplitude and intensity, having looked previously at wavefronts and rays, and we have solved problems involving amplitude, intensity, and the inverse square law, and we've looked at these 2 data booklet equations. Thank you very much.